Right now, as you read these words, something extraordinary is happening. Photons, tiny messengers of light, are racing from your screen to your eyes at 299,792,458 meters per second. Not a fraction faster, not a hair slower, always exactly that speed. Why? This isn't just trivia. This cosmic speed limit is the reason time exists as we know it. Why you can't send a text message to your past self, and why the universe doesn't collapse into paradoxical chaos. The speed of light isn't just fast, it's the scaffolding holding reality together. Tonight, we're going to uncover one of physics' most elegant mysteries: why the fastest thing in the universe can't go any faster. And trust me, the answer will change how you see everything, from your smartphone to the stars above. So, settle in, close your eyes if you like, and let's take a journey through the cosmos at exactly 299,792,458 meters per second. Light is something we all think we understand until we try to explain it. You flip a switch, and there it is, filling the room, letting you see the world around you. But what is it really? The answer: it's both everything and nothing at once. The dual nature of light is made of photons, tiny packets of energy that zoom through space at the universe's ultimate speed limit. But these aren't particles like marbles or peas. They have no mass, they never rest. They're also waves, electromagnetic waves, vibrations of electric and magnetic fields oscillating at right angles to each other, dancing through space in perfect rhythm. This wave-particle duality stumped physicists for centuries. Is light a particle or a wave? The answer broke the rules. It's both, always, simultaneously, depending on how you look at it. Think about it this way: shine light through a single narrow slit, and it behaves like a wave, spreading out in a predictable pattern. But try to measure exactly where a photon hits a detector, and it acts like a discrete particle, making a single point of impact. The universe refuses to let light be just one thing. It's as if reality itself is saying, why choose when you can be everything? This isn't just theoretical mumbo-jumbo. Scientists have actually watched single photons behave both ways. In the famous double-slit experiment, individual photons seem to know whether both slits are open or just one, changing their behavior accordingly. It's like each photon is simultaneously a wave exploring all possibilities and a particle making definite choices. Welcome to quantum mechanics, where the universe gets delightfully weird. Light doesn't need permission to travel. Here's what makes light truly special: it needs no medium. Sound needs air, water waves need water. But light just goes. It travels through the vacuum of space without a problem. That's how we can see the sun, over 93 million miles away. Its light crosses the emptiness between us, without a single rest stop. The electromagnetic spectrum, light's many faces visible light. The rainbow of colors we can see is just a tiny sliver of the electromagnetic spectrum. Imagine a piano stretching for miles. Visible light is just a handful of keys in the middle. On one end, you have radio waves, long, lazy undulations that can stretch for miles. On the other end, gamma rays, sharp, high-energy spikes found near exploding stars and nuclear reactions. In between, microwaves cooking your leftovers, infrared what your TV remote uses, ultraviolet giving you sunburns, and X-rays seeing through your bones but somehow never finding your missing socks. Despite all these differences, they all move at the same speed in a vacuum: 299,792,458 meters per second, about 300,000 kilometers every single second. Light could jog around Earth more than 7 times in a single second. When light slows down, in a vacuum, light has a clear track, but when it passes through water, glass, or diamond, it slows down. Not because it's tired, but because it's interacting with the material's atoms. Like walking through a crowded room. You're still heading the same direction, but there's more bumping and weaving. This slowing causes refraction, the bending of light when it moves from one material to another. That's why a straw looks bent in water or why diamonds sparkle brilliantly. Individual photons still travel at the same speed between atomic interactions. They're just taking a more complicated path, like speed walking through a wedding dance floor full of enthusiastic uncles. Here's something fascinating. Different materials slow light by different amounts. Water reduces light speed to about 75% of its vacuum speed. Glass drops it to roughly 67%. And diamond? Diamond slows light to less than 42% of its maximum speed. That's why diamonds are so sparkly. Light bounces around inside them at reduced speed, taking longer paths, creating that brilliant fire. Scientists have even managed to slow light down to a walking pace in specially prepared materials. In 1999, physicist Len Howe slowed light to just 17 meters per second, slower than a bicycle, by passing it through a supercooled cloud of sodium atoms. And in 2001, she actually stopped light completely, holding it frozen in place before releasing it again. It's like capturing lightning in a bottle, except the lightning is made of pure information, and the bottle is made of quantum mechanics. Color, your brain's best guess. When you see a rainbow, you're watching light split into various wavelengths. Red is long and lazy, violet is short and twitchy. Your eyes have special cells, cones tuned to specific wavelength ranges. The apple isn't red. It's reflecting the wavelength we interpret as red while absorbing the rest. Color is your brain's educated guess based on which vibrations reach your retinas. The photon's eternal motion light has no rest mass. Unlike you, me, or your cat, it doesn't need energy to move. It always moves, it has no choice. If a photon stopped, it wouldn't just be taking a break, it would cease to exist. Motion or nothing, all or gone. This is the traveler we're following tonight. Massless packets of energy that behave like waves and particles, traveling at a universal speed, delivering sight and color to conscious beings like us. Light isn't just what helps us see, it's how the universe whispers its story into our eyes. For most of human history, people believed light moved instantaneously. The sun rose and the world turned golden. No waiting, no delay. It seemed obvious. Even Aristotle, whose opinion stuck around for centuries, thought light was instantaneous. Case closed. Galileo's adorable attempt, 1638. But Galileo wasn't one to accept things just because someone important said so. Around 1638, he tried to measure light speed in what might be the most endearingly optimistic experiment in history. He and his assistant each took a lantern and stood on hilltops about a mile apart. Galileo would uncover his lantern, and as soon as his assistant saw the light, he'd uncover his in return. Galileo would measure the time between sending and receiving. The problem? Human reaction time is about a quarter of a second. Light takes less than a 10,000th of a second to travel a mile. It's like trying to measure a bullet's speed with a sundial. Galileo concluded that if light had a finite speed, it was far too fast to measure, which was true. But at least the question had been asked. Ole Rømer's breakthrough, 1676. Fast forward to Danish astronomer Ole Rømer, who in 1676 accidentally stumbled upon the answer by watching Jupiter's moon, Io. He noticed something odd. Io's appearances from behind Jupiter weren't consistent. Sometimes it appeared late, sometimes early. Rømer had a brilliant thought. What if it wasn't Io being inconsistent, but us? What if the delay was caused by Earth being sometimes farther from Jupiter, meaning light from Io had farther to travel? From these timing discrepancies, Rømer estimated light took about 22 minutes to cross Earth's orbit diameter, about 186 million miles. Not perfect, but revolutionary. It told the world, light takes time. Not much, but enough to matter. Fizeau's spinning wheel, 1800s. In the early 1800s, physicist Hippolyte Fizeau tried something more earthbound. His method involved a light beam, a rotating toothed wheel, and a mirror several miles away. The beam passed through a gap between teeth, traveled to the mirror, and bounced back. If the wheel spun slowly, returning light passed through the same gap. But if it spun faster, the returning light hit a tooth and was blocked. By adjusting the wheel speed to the point where light was completely blocked, Fizeau calculated light's speed at about 313,000 kilometers per second, close enough to shake the scientific world. Michelson's precision, late 1800s, Albert Michelson took this further, using long tunnels, carefully aligned mirrors, and incredibly precise timing. His efforts earned him the 1907 Nobel Prize in Physics, the first American to receive it. Not bad for chasing light beams with mirrors. The modern definition today, we've flipped the equation entirely. Since 1983, the meter has been officially defined as the distance light travels in 1/299,792,458th of a second. We no longer measure light's speed, we use it as the standard to measure everything else. The speed of light isn't just a number. It's a story of curious minds, imperfect tools, and elegant persistence across centuries. So why doesn't light just go faster? Why 299,792,458 meters per second? Why not 500 million? Why not infinite? Maxwell's equations. The hidden answer, 1860s. To understand this, we meet James Clerk Maxwell. In the 1860s, Maxwell took everything scientists knew about electricity and magnetism and turned it into 4 elegant mathematical equations, Maxwell's equations. These equations describe how electric and magnetic fields interact, change, and move. But here's the dreamy part. When Maxwell combined them, they predicted electromagnetic waves that would naturally emerge whenever electric and magnetic fields wiggled in just the right way. And these waves would always travel at a specific speed. When Maxwell plugged in the known values for electric and magnetic constants, he got a number, 299,792,458 meters per second. That number matched the best measurements for light speed. This wasn't coincidence, it was revelation. Light, Maxwell realized, was an electromagnetic wave, a self-propagating ripple of electric and magnetic energy. Its speed wasn't random. It was built into the equations governing reality itself. Imagine Maxwell sitting at his desk, pen in hand, working through these equations. He's probably not expecting anything earth-shattering, just trying to organize what's known about magnets and electric charges. Then suddenly, the math starts telling him something wild. There should be waves. Waves made of intertwined electric and magnetic fields, constantly regenerating each other as they move. A changing electric field creates a magnetic field. That changing magnetic field creates an electric field. Back and forth, leapfrogging through space, each field creating the other in an eternal dance. It's like the universe discovered perpetual motion, but for fields instead of machines. And when Maxwell calculated how fast these waves should move, using only the properties of electricity and magnetism, things scientists had measured in laboratories with coils and batteries, he got the speed of light, not approximately. Exactly, it was one of those rare moments in science where everything clicks into place. Suddenly, light wasn't mysterious anymore. It wasn't some separate phenomenon that just happened to exist. It was electricity and magnetism joined together, moving through space according to mathematical law. Light speed isn't a habit, it's fundamental architecture. If electric and magnetic fields exist, and they do, then light must travel at this speed. Anything faster or slower would break the laws as we understand them. Einstein's special relativity, 1905, but why can't anything go faster? In 1905, Albert Einstein published his special theory of relativity, changing everything. One key postulate: the speed of light in a vacuum is the same for all observers, no matter how fast they're moving. This sounds tame, but is actually bananas. Imagine you're on a spaceship moving at 90% light speed. You turn on a flashlight. You might expect that light would appear faster to someone standing still. After all, you're already moving and adding the flashlight beam on top. But nope. Both you and the stationary observer measure that light beam at exactly 299,792,458 metersconts, not a hair more, not a flicker less. To make this possible, reality bends itself around this rule. Time slows down, lengths contract, mass increases. The universe changes how it ticks to ensure no one can ever observe light speeding up or slowing down. Here's what makes this truly mind-bending. Einstein didn't discover this by doing experiments. He discovered it by thinking. He was a 26-year-old patent clerk, examining applications during the day and pondering the universe at night. He asked himself simple questions. What would it be like to ride alongside a beam of light? If you could match light's speed, would the light wave appear to stand still? According to Maxwell's equations, that shouldn't be possible. A stationary electromagnetic wave doesn't make sense. It would violate the fundamental laws of electromagnetism. So Einstein made a bold leap. Maybe you can never catch up to light. Maybe no matter how fast you go, light always moves away from you at exactly the same speed. But if that's true, something else has to give. And that something is everything we thought we knew about time and space. Think about two events happening in space: a light turning on here and a bell ringing over there. In everyday life, we assume everyone agrees on whether they happened at the same time. They might disagree on where the events happened, depending on their position, but surely they'd agree on when. Einstein said no. If the speed of light is the same for everyone, then simultaneity itself must be relative. Two events that happen at the same time for you might happen at different times for someone moving past you. Time itself is not universal. It's personal, local, flexible. It's as if the universe looked at all the things we thought were fixed: time, space, simultaneity, and said, actually, all of these can bend. But this one number, this speed of light, that's sacred. The infinite energy problem: if you tried to accelerate to light speed, you'd run into a problem. As you get faster, your mass increases. Not from eating too many cookies, but in the you require more energy to go just a bit faster sense. As you approach light speed, your mass trends toward infinity. You'd need infinite energy to reach it. Infinite energy is a tall order, so no matter how hard you try, you can get close but never quite there. You can chase light, but you'll never catch it. Why? This limit saves reality. If light's speed weren't limited, causality would break down. You could theoretically see effects before causes or send information backward in time. Chaos, time travel paradoxes, a serious headache for logic. Instead, the universe protects us with this beautiful speed cap. It keeps things ordered, predictable, calm. No matter what else changes, light speed stays the same. The speed of light is the cosmic speed limit, the upper bound on how fast information, energy, or anything with mass can travel. It's a boundary fundamental to space-time itself. Light doesn't go faster because it can't. Not because it's weak, but because it's perfect exactly as it is. Bound to a speed that keeps time flowing forward, keeps causality intact, and lets us understand the world. For something zipping across space at nearly 300,000 kilometers per second, that's a pretty graceful pace. When Einstein introduced special relativity in 1905, he didn't just tweak physics, he rewrote it. At its heart was a bold statement. The speed of light in a vacuum is constant. Not generally constant, not pretty consistent, absolutely constant. For everyone, everywhere, always. This breaks everything you think you know about motion and time. The weird consequences: let's say you're floating peacefully in a spaceship. You turn on a flashlight. Light shoots out at 290,792,458 meterseconds. Now imagine someone else flying past you in another spaceship at half light speed, From their perspective, you're whizzing by like a blur. But when they measure your flashlight beam, they don't see it moving faster. They also measure it at exactly 290,792,458 milliseconds. That's deeply weird. In the everyday world, speeds add up. If you walk on a moving sidewalk, your speed is walking speed plus belt speed. But with light, the sidewalk could be moving, the person could be moving, the flashlight could be moving, and light speed stays the same for all of them. Einstein's solution, it's not light speed that changes, it's everything else. Time, space, the passage of moments, the size of things, all of it bends to preserve that one sacred number. Time dilation. The slower you age, the faster you move, the slower time passes for you compared to someone at rest. This is real and measurable. Example, you're on a spaceship traveling at 90% light speed. To you, everything feels normal. You eat snacks, read a book, wonder why you didn't pack more socks. But when you return to Earth, much more time has passed for everyone else. Years, even decades. While you experienced a short trip, Earth aged without you. We've tested this. Particles called muons, created high in Earth's atmosphere, decay in microseconds. But when moving near light speed, their internal clocks slow down. They last longer, long enough to reach the ground and be detected. Time actually stretches for them. But it's not just subatomic particles. We've tested this with actual clocks too. In 1971, physicists Joseph Huffalet and Richard Keating did something wonderfully straightforward. They took atomic clocks on airplane flights around the world. One set of clocks flew eastward, in the direction of Earth's rotation. Another set flew westward, against it. A third set stayed on the ground. When the planes landed and the clocks were compared, they showed different times. Not by much, we are talking nanoseconds, but exactly the amount predicted by relativity. The eastward clocks, which had been moving faster relative to Earth's center, ran slightly slower. The westward clocks ran slightly faster. The predictions matched reality to within the margin of error. Think about what this means. Every time you take a flight, you age slightly less than people on the ground. By a handful of nanoseconds, sure, but the effect is real. Frequent flyers are literally time travelers, aging microseconds less than their friends who stay home. Not exactly a fountain of youth, but technically accurate. And astronauts on the International Space Station? They're moving much faster, about 28,000 kilometers per hour. After 6 months in orbit, an astronaut has aged about 0.007 seconds less than people on Earth. It's tiny, but it's real. Time itself moves differently for them. Length contraction. Space gets squishy. When you travel at high speeds, objects in your direction of motion appear shorter, not by optical illusion, by physical reality. Your spaceship would literally measure shorter along its travel path. This only becomes noticeable at speeds close to light speed. For everyday travel, cars, planes, enthusiastic joggers, the effect is so small it might as well not exist. But near light speed, the universe gets squishy. Relativity of simultaneity. When now gets complicated, two events that happen at the same time for one person might not happen simultaneously for another if they're moving relative to each other. Imagine a train moving very fast. In the middle, a light bulb flashes. From the passenger's view, light reaches the front and back simultaneously. But from the platform, light reaches the back first because the front is moving away from the flash. Both observations are correct. Time and space are no longer universal. They're flexible, local, relative. Why this matters? Protecting causality, this cosmic speed limit, protects our sense of before and after. Because light can only travel so fast, information can only travel so fast. You can't see an event before it happens. You can't send a message into the past. Without this limit, you could cause effects before their causes. You could receive messages before someone sent them. paradoxes would pile up. Instead, the universe gently says, no, let's have order. Let's have a maximum speed. Let's make it sacred. Real-world applications today, GPS satellites rely on Einstein's equations. The satellites move quickly relative to Earth's surface, so their clocks tick slower. Special relativity. But they're higher in Earth's gravitational field, making time tick faster. General relativity. Without correcting for both effects, your GPS would be wrong by several kilometers every day. Thanks to Einstein and light's constancy, your GPS can tell you which turn gets you to that bakery. This isn't just theory living in books. It's reality, tested and proven, guiding everything from particle accelerators to astronomy to your phone's navigation. The speed of light isn't just a limit on speed. It's a cornerstone of reality, the cosmic scaffolding holding up time and space. Once you realize light can't go faster than it already does, the implications ripple outward, touching everything from how we understand time to how we view the night sky. The light cone, your cosmic neighborhood light speed, gives time a structure. It draws boundaries around what can influence what. This is the light cone. Imagine lighting a match in a field. Light spreads in every direction. The furthest anything can be affected by that match is limited by how far light can travel from that moment onward. If someone is 100 light years away, they won't even know the match was lit until 100 years later. Flip it. The only events that could possibly influence you right now are those whose light has had time to reach you. That's your past light cone. Everything that could have caused your present moment. The light cone isn't just a diagram. It's the border between possible and impossible. If something happens outside your light cone, it's not just too far away. It's too far away in time. No signal can reach you yet. It's as if it doesn't exist for you until the light arrives. The night sky, a time machine. When you look at stars, you're not seeing them as they are. You're seeing them as they were. Alpha Centauri's light takes over 4 years to reach us. If something dramatic happened there last week, we won't know for several more years. The Andromeda Galaxy's light takes over 2 million years to arrive. You're seeing it as it looked when early humans were figuring out how to make tools. Look further and you see light that left its galaxy billions of years ago, before our sun existed. Yet it feels so present. Stars twinkling, galaxies glowing. This delay allows astronomers to be time travelers. When they look into deep space, they're not just looking far, they're looking back. Every telescope is a time machine peering into epochs long gone, enforcing causality. You can't influence something unless there's time for a signal to get there. This isn't just a rule, it's a safeguard preventing paradoxes. If you could send signals faster than light, you could theoretically message your past self. Don't eat that suspicious burrito. If you listened, you'd have no reason to send the message. That's a logic loop that keeps physicists up at night. But with light's speed cap, those loops never happen. You can't outrun your own consequences. Events happen in order. The past stays behind you, the future ahead. Everyday delays, this affects daily life too. When you make a phone call across the planet, there's a slight delay, tiny but measurable. The signal travels as electromagnetic waves, often through satellites or fiber-optic cables. These waves move at or near light speed, but Earth is big and light still takes time. When Mission Control sends a signal to a Mars rover, it can take 4 to 20 minutes to arrive, depending on planetary positions. If the rover stubs its robotic toe, scientists won't know until nearly half an hour later. No real-time remote control. The rover must be autonomous because light speed says, you're on your own out here. Structure and harmony, light speed might seem like a constraint, but it's really a kind of harmony. It gives us a universe where effects follow causes, where the past is fixed and the future waits. It turns an endless void into a tapestry of ordered events. That delay, those tiny moments of waiting, make the universe understandable. They give us distance, perspective, a little room to think, and maybe a little space to rest. Naturally, humans have a habit of pushing limits. We've broken the sound barrier, sent robots to Mars, smashed atoms apart. So what's stopping us from finding a cosmic shortcut that goes faster than 299,992,458 meters seconds? Tachyons. The theoretical speedsters tachyons are hypothetical particles that can only travel faster than light. They can't slow downtown to reach light speed. That's their limit in the other direction. Sounds exciting, right? A particle that naturally ignores the speed limit. There's one problem. No one has ever found a tachyon, not in a lab, not in deep space, not lurking in equation gaps. They're like a rumor, always mentioned, never seen. Even if tachyons existed, they'd cause problems. If you could use them to send information, you'd violate causality, sending messages into your own past. Physicists mostly agree. Tachyons are fun to think about, but probably not real. They belong in the interesting but note box. Quantum entanglement. Spooky action. When two particles are entangled, measuring, one seems to instantly affect the other, no matter how far apart they are. Measure one on Earth, and its twin on the other side of the galaxy reacts in perfect sync. Surely this is faster than light? Yes and no. While entanglement correlations appear instantly, they don't transmit usable information. You can't control the measurement outcome, so you can't use it to send a message. It's like two people flipping identical coins across the universe and somehow always getting matching results. But neither can use it to say hello. Einstein called it spooky action at a distance. Modern experiments confirm entanglement is real and that it doesn't allow faster than light communication. The universe is spooky but still respects the speed limit. Cherenkov radiation. The local speedster Cherenkov radiation happens when a charged particle moves through a medium like water faster than light can move through that same medium. Yes, you heard that right. Light doesn't always move at full speed. In materials like water or glass, it slows down due to atomic interactions. If a particle moves faster than that reduced speed, it creates a light shockwave, similar to a sonic boom. This causes the eerie blue glow in nuclear reactors submerged in water. But nothing's breaking the universal speed limit, just the local speed limit inside the material. Light in a vacuum still reigns supreme. No laws broken, just bent a little in the pool. Warp drives, bending space. Could we build a warp drive like in science fiction? Could we bend space itself instead of moving through it? In theory, maybe. Physicist Miguel Alcubierre suggested contracting space in front of a spacecraft and expanding it behind. The ship would ride a wave of warped spacetime, technically never moving faster than light through space, but arriving quicker than a light beam on its own. Clever workaround, but it has snags. It requires negative energy density. Exotic matter we have no evidence for energy requirements would be astronomical. Some calculations suggest Jupiter's mass energy just to move a grapefruit. For now, warp drives remain firmly in imagination's realm. Wormholes, cosmic shortcuts. Wormholes are theoretical tunnels through space-time connecting two distant points instantly. Think cosmic shortcuts or space-folding bridges. The math allows for them, but problems stack up. Stability, exotic matter, time paradoxes. It's like building a suspension bridge with soap bubbles and hope. Even if you could make one work, it wouldn't technically be faster than light travel, just a shorter path. Light still wins the marathon. You just found a convenient side street. The verdict, despite clever ideas and curious exceptions. Nothing with mass or information has ever been observed traveling faster than light. Every time we think we've found a loophole, the universe calmly closes it with a raised eyebrow and equations. Maybe that's not such a bad thing. Light speed might seem like an irritating restriction, but it's more like a safety rail keeping the universe from falling into paradox and chaos. It gives us structure, order, and cosmic serenity, knowing that even the universe won't cross certain boundaries. If you ever wish you could beam across stars or message your past self, take comfort. Light itself, swift, silent, steady, is already moving as fast as anything can. It's leading the way. And perhaps that's enough. By now, you might sense a pattern. Light speed isn't just an arbitrary number, it's a cosmic foundation stone woven into the universe's architecture. The conversion factor between space and time. The speed of light, c, is not just a photon's pace, it's a bridge between space and time. That number lets us translate distance into time and back again. It's the universe's built-in translator. You've seen this in Einstein's EMC squared. Here, light speed bridges mass and energy, showing how much energy is locked in a certain amount of mass. But c also appears everywhere in relativity. Equations describing time dilation, length contraction, space-time curvature. It keeps popping up because it's more than just speed, it's universal glue. Space-time, the woven fabric. Imagine the universe as a woven fabric made of both space and time. Not two separate threads, but one single material. Space-time. In Einstein's theory, space and time aren't separate. They're interlinked, behaving like one smooth, flexible thing. When you move through space, you're also moving through time. When you speed up, time slows down. When gravity pulls, it bends both space and time. Light speed is the conversion rate between space and time, like an exchange rate, but instead of euros and dollars, it's meters and seconds. This helps explain why we measure distances in light years. 1 light year is how far light travels in 1 year. The fact we use a time-based unit to describe distance shows how deeply interwoven the concepts are. Natural units. Setting c to 1, physicists don't even treat c as just speed anymore. In many natural units used in theoretical physics, they set light speed to 1. Not because they're lazy, but because it simplifies things. Once you do that, space and time can be treated equally. Distances and durations measure in the same units. Equations get cleaner, more elegant. The universe tidies itself up. Light's perspective, timeless. Here's a wild idea. When light travels, it doesn't experience time. From a photon's perspective, the moment it's emitted and the moment it's absorbed happen at the same instant. There's no ticking clock inside a beam of light. Time, from light's point of view, simply doesn't pass. The faster you go, the slower your clock ticks. For something moving at light speed, ticking stops altogether. It exists only in motion. It's never at rest, it can't be. The meter defined by light since 1983. The meter has been defined by how far light travels in a certain time. 1 meter is the distance light travels in 1,299,792,458th of a second. We've made light speed the ruler against which all rulers are measured. It's our measuring stick for both time and space. The grounding truth in a universe that can seem vast and strange, filled with dark matter and quantum uncertainty. There's something beautifully fixed. Light speed is a constant you can build your world around. We quite literally do. Light doesn't just illuminate the world, it sets the rhythm of the cosmos. And perhaps on a quiet night, as photons from distant stars drift gently down, you can imagine the universe whispering in its own language. Softly, steadily, at exactly 299,792,458 meters per second. The speed of light isn't just floating between galaxies or bouncing off distant stars. It's woven into your everyday life. Even if you've never flown a spaceship or built a particle accelerator in your backyard, you're still living in a world shaped, defined, and quietly orchestrated by light speed. Your phone and the internet, every time you tap your screen, stream a video, or send a sleepy emoji, you're harnessing light's power. Specifically, light traveling through fiber-optic cables. These slender glass or plastic strands form a global web carrying information at nearly light speed. When you load a web page, you're waiting for pulses of light, tiny flashes representing ones and zeros, to journey through cables, bounce through routers, and arrive at your screen. While light speed in fiber is slightly slower than in vacuum, about 2-3 as fast, it's still astonishingly quick, hundreds of thousands of kilometers per second. That's how your cat videos, weather updates, and bedtime playlists arrive with barely a pause. But here's something most people don't realize. Even at near light speed, there are noticeable delays over long distances. When you video call someone on the other side of Earth, say, from New York to Singapore, your signal has to travel roughly 15,000 kilometers. Even at light speed, that's about 50 milliseconds one way. That might not sound like much, but it's enough that you notice it in conversation. That slight pause before the other person responds. That's partly light speed. Your words have to travel thousands of kilometers as pulses of light, get processed and return. The speed limit of the universe is showing up in your video chat. For online gaming, this delay, called ping or latency, can be the difference between victory and defeat. When gamers talk about playing on servers with low ping, they're essentially asking for shorter distances, so light has less far to travel. They're fighting against the fundamental speed limit of information. And it gets even more interesting with satellite internet. Traditional satellite internet uses satellites in geostationary orbit, about 35,000 kilometers above Earth. Your signal has to travel up to the satellite and back down, covering about 70,000 kilometers. Even at light speed, that's roughly 240 milliseconds just for the signal to make the round trip. That's why satellite internet conversations often have that awkward delay. This is why companies like SpaceX are launching satellites much closer to Earth, only about 550 kilometers up. It's not just about coverage, it's about fighting the speed of light to reduce latency. Even light needs time to travel, and in our hyper-connected world, every millisecond counts. GPS. Relativity in your pocket GPS is one of the technologies most reliant on light speed. When you use GPS to find the nearest bakery, your device connects to at least 4 satellites orbiting Earth. Each satellite sends a signal with a nanosecond precision timestamp. Your GPS receiver compares arrival times to triangulate your location. But here's the twist. For this to work, we must account for both special and general relativity. Satellites move quickly relative to Earth's surface, so their clocks tick slower, special relativity. But they're higher in Earth's gravitational field, making time tick faster, general relativity. Without correcting for both effects, your GPS would be wrong by several kilometers every day. Thanks to Einstein and light's constancy, your GPS guides you to that croissant you're craving. Vision. Light in your eyes, vision itself is built on light's behavior. When you look at the world, photons bounce off objects and enter your eye. These photons travel through your cornea and lens, focus on your retina, and trigger chemical changes in cells called rods and cones. Your brain reconstructs these electrical signals into vivid, colorful images. A tree, a sunset, your oddly judgmental houseplant. All of this depends on how fast light travels, how it bends through materials, and how it interacts with retinal atoms. Even depth and motion perception rely on the delay between light reaching each eye. Here's something wild. You never see anything in real time. Everything you see is technically in the past. When you look at someone sitting across from you, you're seeing them as they were a few nanoseconds ago. The time it took light to bounce off them and reach your eyes. For nearby objects, this delay is imperceptible, but it exists. Look at the moon, and you're seeing it as it was 1.3 seconds ago. The sun, 8 minutes and 20 seconds in the past. If the sun suddenly vanished right now, we wouldn't know for over 8 minutes. We'd still see it shining, still feel its warmth for a bit, completely unaware that our star was already gone. But here's where it gets really interesting. Your brain knows about this delay, and it compensates. When you catch a ball, your brain predicts where it will be, accounting for the tiny lag between light leaving the ball and reaching your eyes. When you look at a moving object, your visual system actually shows you where it's likely to be now, not where it was when the light left it. Your brain is constantly doing relativistic corrections, accounting for light's travel time, filling in gaps, and presenting you with a seamless experience of now, even though you're technically seeing the past. Every moment of vision is your brain's best guess about reality based on information arriving at light speed. And consider this: different colors of light travel at the same speed in vacuum, but they slow down by different amounts in materials. Blue light slows more than red light in glass. This is why prisms create rainbows. Different colors bend different amounts when entering and leaving the glass. It's called dispersion, and it's why the sky is blue, why sunsets are red, and why that rainbow appears after a storm. All of it comes down to how light of different wavelengths interacts with matter. Refraction. Bending reality, consider refraction, how light slows down and changes direction entering different materials. This makes straws look bent in water or creates shimmering effects on hot roads. It's also the principle behind eyeglasses, microscopes, telescopes, and camera lenses. Every time you snap a photo or read with glasses, you're benefiting from our understanding of light's travel. Microwaves, heating through light. Even the microwave oven owes its existence to electromagnetic waves. Microwaves are just lower frequency light. They bounce inside the oven, causing water molecules in food to jiggle and heat up. Without the electromagnetic spectrum and our understanding of light's properties, reheating leftovers would be far messier. Telecommunications. The light family your favorite radio station? That's just light with longer wavelengths. Radio waves are part of the electromagnetic spectrum, traveling at the same vacuum speed, allowing your car to belt out music. Television broadcasts, Wi-Fi signals, Bluetooth connections, all are forms of electromagnetic radiation zipping through space, guided by the same rules governing starlight and lasers. Medical imaging. Seeing inside X-rays, those ghostly bone images are high-frequency electromagnetic waves passing through soft tissue, but absorbed by denser materials like bone. That contrast gives us skeletal snapshots. MRI machines, while not using light directly, rely on electromagnetic fields to create detailed body images. Light, or its extended family, is quietly working behind the scenes in nearly every area of modern life. How we see, communicate, navigate, cook, stream, scan, and study the stars. Astronomy, light as messenger. Everything we know about the universe beyond our solar system has been delivered by light. Telescopes like Hubble capture faint photons that have traveled billions of years across space. These ancient beams carry encoded stories about galaxies, nebulae, black holes, and the early cosmos. We decipher them by analyzing color, intensity, and spectrum. A small wavelength shift, redshift, tells us how fast a galaxy moves away. A slight brightness dip hints at a planet passing in front of its star. A strange background glow might be a Big Bang whisper. It all works because light obeys the same rules everywhere, whether bouncing off your coffee mug or arriving from a galaxy 13 billion light years away. But there's something profoundly beautiful about astronomical observation that deserves more attention. We're not just looking at space, we're looking through time. When the James Webb Space Telescope peers into the deepest reaches of space, it's not looking at what's happening now. It can't. It's looking at what was. Some of the galaxies it images existed when the universe was only a few 100 million years old. Infant galaxies in a young cosmos. Here's the mind-bending part. Those galaxies don't look like that anymore. In fact, many of them probably don't exist at all anymore. They might have collided with other galaxies, been torn apart by gravitational forces, or evolved into something completely different. But we see them as they were because that's when the light left them. The universe has a built-in archive system. The farther you look, the farther back in time you see. Every distance is also a date. And consider this, because the universe is expanding, some galaxies are moving away from us so fast that their light is being stretched into longer and longer wavelengths. Eventually, some galaxies will be moving away faster than light can reach us, not because they're violating the speed limit. Space itself is expanding between us, but the effect is the same. Their light will never reach us. There are parts of the universe we will never see, stories we will never read, simply because the universe is too big and expanding too fast. But what we can see is extraordinary. In 2019, scientists released the first image of a black hole, or rather the glowing material around it. That black hole is in the galaxy M87, about 55 million light-years away. The light we captured left that black hole 55 million years ago, when dinosaurs still roamed Earth. By the time that light completed its journey across space, dinosaurs had gone extinct, continents had shifted, and humans had evolved enough to build radio telescopes to catch it. Every photon is a time capsule. Every telescope is a time machine. And the speed of light is what makes it all possible. The quiet dance. So next time you open an app or look at the moon, marvel at what's really happening. The quiet, graceful dance of photons, electromagnetic fields, and universal constants. The steady, tireless motion of light racing around, through, and within your world, all at 299,792,458 milliseconds. Light isn't just a cosmic phenomenon, it's in your pocket, in your home, in your eyes. It's the quiet engine of the everyday. Take a moment to imagine a single beam of light drifting through vast emptiness. No planets, no stars, no gravity. Just one solitary photon gliding effortlessly through vacuum, neither speeding up nor slowing down. It has no mass, no rest, no need for fuel. It simply exists in motion, moving at the only speed it knows, 299,792,458 meters per second. That image is more than poetic, it's a glimpse into the fabric of the universe. This humble light beam is participating in the great cosmic symphony, a dance of information, energy, and time weaving everything we know. The cosmic microwave background, ancient light. The oldest light in the universe is the cosmic microwave background, CMB faint, uniform glow filling the universe, bathing everything in its presence. It's not light from stars or galaxies. It's the cooled remnant of the moment the universe became transparent, about 380,000 years after the Big Bang, when things cooled enough for atoms to form and photons to roam free. Before that, the universe was like dense fog, opaque, chaotic, hot. But once neutral hydrogen formed, light could move without constant interference. So it did. It set off in all directions, a sea of ancient radiation now stretched by cosmic expansion into soft microwave whispers. When scientists measure the CMB, they're catching photons that have traveled since the dawn of time. These light particles have never rested. They've crossed the universe just to land in a detector and say, "Here's what it was like back then." That's not just history, it's cosmic archaeology. What's remarkable is that these photons have been traveling for 13.8 billion years, and they're still going strong. They've witnessed the birth of the first stars, the formation of galaxies, the creation of our solar system, the evolution of life on Earth, all while simply moving through space at their constant speed. And we can read their story. The CMB isn't perfectly uniform. It has tiny temperature variations, about 1 part in 100,000, that represent the seeds of all cosmic structure. Regions that were slightly denser became the locations where galaxies eventually formed. Regions that were slightly less dense became the voids between galaxy clusters. In 1964, Arno Penzias and Robert Wilson accidentally discovered this cosmic background while trying to eliminate annoying noise from their radio antenna. They kept detecting a persistent hiss coming from every direction in the sky. They checked for birds nesting in the antenna. There were some, which they politely removed. They pointed the antenna in different directions. They cleaned everything. The hiss remained. Turned out they weren't detecting noise. They were detecting the echo of the Big Bang itself. Light that had been traveling for nearly 14 billion years just to create a gentle static in their equipment. They won the Nobel Prize for finding the most important signal that was initially mistaken for the most annoying noise. Photosynthesis, light fueling life, binds everything we experience. Take photosynthesis, the engine behind almost all Earth life. It starts when sunlight hits a leaf. Photons strike chlorophyll molecules, exciting electrons and triggering reactions that store energy in chemical bonds. Plants use this energy to grow. Animals eat plants or eat the animals that eat plants. The chain of life continues. Without light, there's no photosynthesis. Without photosynthesis, no plants. Without plants, dinner gets a lot less interesting. In a real sense, every meal you've ever eaten started with a photon from the sun. But let's appreciate just how remarkable this process is. When a photon from the sun, which began its journey in the solar core about 8 minutes earlier, strikes a chlorophyll molecule in a leaf, it's completing an incredible journey. That photon was created deep inside the sun through nuclear fusion. Took thousands of years to random walk its way from the core to the surface, bouncing off atoms the whole way. Then spent 8 minutes crossing 93 million miles of empty space, passed through Earth's atmosphere, and finally struck exactly the right molecule to trigger the exact chemical reaction needed to sustain life. And this happens billions upon billions of times every second in every green plant on Earth. The energy in that photon gets converted into chemical energy, specifically into molecules of glucose, sugar. That glucose might be used immediately by the plant to grow, or it might be stored for later. An animal might come along and eat the plant, breaking down that glucose to power its own cells. You might eat that animal. Eventually, the energy from that single photon, created in the sun 8 minutes ago, powers your thoughts, your heartbeat, your ability to read these words. Every movement you make, every thought you think, every breath you take, all of it powered by sunlight, captured by plants, and passed along through the food chain. You are, in a very literal sense, running on solar power. Ancient photons from the sun, converted into chemical energy, converted into the electrical signals in your neurons and the mechanical motion of your muscles. And here's the beautiful part. This has been happening for billions of years. The first organisms to perform photosynthesis appeared roughly 3.5 billion years ago. For most of Earth's history, photosynthesis has been quietly converting sunlight into life. The oxygen you're breathing right now, produced by photosynthesis. The food you ate today, powered by photosynthesis either directly, if you ate plants, or indirectly, if you ate something that ate plants. Life on Earth is fundamentally a system for capturing and using light. We are all children of the sun, sustained by its constant rain of photons, each one traveling at exactly 299,792,458 meters per second. Circadian rhythms. Light as timekeeper, our bodies are built to capture and respond to light. The human circadian rhythm, our internal clock, is deeply influenced by light. As sunlight changes through the day, it regulates sleep, alertness, mood. Morning light tells your brain to stop producing melatonin, the sleepiness hormone. In the evening, fading light lets melatonin rise, nudging you toward rest. Your body is tracking light around you, adjusting rhythms, syncing to the world's subtle cues. Light as connection, but perhaps light's most profound role is connection. It connects not just eyes to objects or stars to telescopes, but moments to each other. It's how information travels. Every time we see something, across a room or across the sky, we're receiving messages encoded in waves, shaped by space, translated by our minds. Light is the language of the universe. And like any language, it has dialects, different wavelengths for different stories. Some tell us about distant galaxy chemical compositions. Others warn of gamma ray bursts, the most energetic universe explosions. Some carry warmth from newly formed stars. Others paint rainbows across oil slicks and soap bubbles, revealing hidden interference and refraction geometry. Think about what this means for connection. Every handshake, every smile, every loving glance, all of it mediated by light. When you look into someone's eyes, you're seeing photons that bounced off their irises mere nanoseconds ago. Those photons carried information about their expression, their emotion, their presence. Light is literally how we see each other, and it works both ways. The light that lets you see others also lets them see you. Every social interaction, every moment of recognition, every time someone knows you're there, light makes it possible. We are all walking around, emitting and reflecting light, sending out information about ourselves to anyone with eyes to receive it. But light connects us not just to each other, but to history. The light in old photographs, whether they're daguerreotypes from the 1800s or digital images from yesterday, captured specific photons at specific moments. Those photons bounced off people who are now gone, places that have changed, moments that can never return. Photography is, in essence, the art of catching light and holding it still. And consider the light from stars again, but in a different way. Every atom of carbon in your body was forged in the heart of a dying star billions of years ago. That star shone brightly, radiating light into space. Eventually, it exploded, sending its atoms, including the ones that would become you, out into the cosmos. Those atoms drifted through space, joined a cloud of gas and dust, collapsed to form our solar system, became part of Earth, entered the food chain, and eventually became part of you. The same process that made that star shine made the atoms you're made of. You are literally made of ancient starlight, not metaphorically, not poetically, but actually. Every breath you take contains atoms that were once in the heart of a star, glowing white hot, generating the light that allowed that star to be visible across the galaxy. You are stardust, animated by the same forces that make stars shine. Learning to listen better. We've learned to listen better. With radio telescopes, we hear hydrogen cloud whispers. With X-ray telescopes, we see galaxy cluster skeletons. With infrared instruments, we peer through dust to watch stars being born. We've even built gravitational wave detectors, tuned not to light but to space-time ripples. Another cosmic messenger complementing what photons have always told us. You are made of star stuff. All this paints a picture of a universe not as cold, silent expanse, but as a place full of signals, stories, light. We're not separate from the cosmos, observing from afar. We're bathed in it, shaped by it, part of it. The atoms in your body were forged in stars that lit up billions of years ago. Light from those stars crossed interstellar space, touched gas clouds, seeded new solar systems. That same process created the carbon in your cells, calcium in your bones, iron in your blood. You are literally made of star stuff, carried to you by light. The restless traveler, this photon, with no mass, no clock, no home, does more than move. It connects ancient past to present moment. It ties atoms to galaxies. It lets eyes see and minds understand. In a universe so vast and full of unknowns, light is a constant companion, not just fast, not just fundamental, but familiar. It's the quiet presence that turns space into story, fills the dark with meaning, and whispers across emptiness. I am still here. Tonight, as you settle in and let thoughts drift with stars, remember, even in quiet, even in dark, light is always on its way. And so here we are, gently floating back to where we began. We set out to answer a simple question: why does light have a speed limit? Along the way, we wandered through photon fields, danced with electromagnetic waves, listened to cosmic whispers, watched time bend and space stretch, saw clocks slow and stars speak in ancient beams. We traveled through cables and galaxies, through your phone, your eyes, and the microwave background's quiet glow. The answer is as elegant as it is profound. Light travels the way it does because the universe is built to let it, and to be shaped by it. Its speed isn't just fast, it's fundamental. A cosmic rule holding everything together from atom pulses to galaxy stretches. It can't be broken or outpaced, and perhaps that's good. Light speed gives us order, it gives us time, it gives us a way to understand. It gives us stories and sunsets and starlight warmth on cold nights. Maybe we don't need it to be faster. Maybe it's already perfect just the way it is. But there's something else worth considering as we close this journey. The speed of light, this constant, unchanging number, is itself a kind of gift. It's what allows the universe to be comprehensible. It's what lets us do science, make predictions, understand cause and effect. Imagine if light speed varied randomly. If sometimes photons moved at one speed, sometimes at another, with no pattern or reason, the universe would be chaos. We couldn't rely on our observations. We couldn't trust our measurements. Physics would be impossible. Instead, we have this beautiful constancy. Wherever you are in the universe, whenever you are in history, light moves at the same speed. It's a universal truth you can count on. In a cosmos that can seem random and chaotic, that's remarkably comforting. And it's not just light. Many of the fundamental constants of physics, the strength of gravity, the charge of an electron, the mass of a proton, all seem to be precisely tuned to allow for complex structures like stars, planets, and living things. Change any of them by even a small amount, and the universe would be unrecognizable. Stars might not form, atoms might not be stable, chemistry might not work. The speed of light is part of this cosmic symphony. It's one note in a larger harmony that makes the universe not just possible, but beautiful. So when you look at light, whether it's the warm glow of a sunset, the cold twinkle of distant stars, or the gentle blue light of your phone screen, remember what you're seeing. You're witnessing a fundamental truth of reality expressing itself. You're seeing the universe being exactly what it is, obeying its own deepest laws, moving at its own perfect pace. And perhaps that's the most profound lesson of all. The universe doesn't need to be different. It doesn't need to be faster or slower, bigger or smaller. It is exactly what it needs to be for us to be here, thinking about it, marveling at it, trying to understand it. Light isn't in a hurry to go anywhere. It's already moving as fast as it's possible to move. And that speed, 299,792,458 meters per second, is written into the very fabric of spacetime itself. It's the speed of causality, the speed of information, the speed of reality itself. The invitation, so wherever you are right now, curled up in bed with stars outside your window, or sitting quietly on the other side of the world with morning light beginning to rise, thank you for spending this time here. If this journey helped you wind down or sparked quiet wonder, share it with someone who might appreciate it too. And if this accidentally kept you awake, At least you learned something interesting while waiting for sleep to find you. The next time you turn on a light, make a phone call, look at the stars, or simply see the world around you, take a moment to appreciate the invisible messenger making it all possible. Light doesn't ask for recognition. It doesn't demand appreciation. It simply does what it's always done, moves through the universe at its constant pace, connecting everything, illuminating everything, making everything visible and knowable. Until next time, rest well.